Hello and welcome to the Amazon Web Services webcast, getting started with the Amazon EC2 container service. I'm Chris Barclay and I'm the product manager. And before we begin, I'd like to walk you through a few items. On your screen, you'll see a Q&A pod. Please submit your questions at any time during the webcast, and our Q&A moderator will address them throughout the presentation. I'll also answer a few in the live Q&A session at the end of the presentation. Today's webcast is being recorded, and we'll send you a follow-up email with the URL to the recording as well as a link to the presentation deck. So, welcome to today's webinar. Again, I'm Chris Barclay, the product manager for Amazon Web Services and the EC2 container service. So today I'm going to take you through a presentation about containers, how they're used by the EC2 container service, some common patterns, and I'll throw a couple of demos in there as well, and then we'll finish off with some Q&A. So containers are similar to hardware virtualization, like what you get with technologies like EC2. However, instead of partitioning a single machine, the containers isolate the processes that are running on an operating system. And this is a useful concept that lets you share an operating system kernel to create multiple isolated user space processes that can have constraints on them like CPU and memory. The Docker CLI using libcontainer makes using containers really easy with commands like docker run to get a container started. And Docker images make it easy to define what runs in a container and conversion your entire application. And these concepts enable container automation. You can define your application, build and share that image, and then deploy that image as well. So you might be thinking, this sounds interesting, but why would I want to use containers? Well, there's 4 key benefits to using containers. The first is that containers are portable. The image is consistent and immutable, so no matter where you run it or when you start it, it's exactly the same. This makes the development lifecycle simpler. An image works the same on the developer's desktop and in production, or whether you start it today or scale your environment tomorrow, so there's no surprises. In addition, the entire application is self-contained. The image that you've created is the version of your app, which makes your deployments and scaling a lot easier because the image includes all of its dependencies. The last part about portability is that Docker images are usually really small, like they're in the tens of megabytes for an image, and so it makes it really easy to share. The other advantage is that containers are flexible. You can create clean, reproducible, and modular environments. Whereas in the past, you might have had multiple processes that would be run on the same operating system, for example, like your Ruby app server, maybe some caching, a log pushing service. Now you can create microservices that make it easy to decompose your application into smaller chunks, reducing complexity and letting your teams move faster while still running the processes on the same host. For example, you don't have to worry about library conflicts when you run 2 different processes in 2 different containers. You can let those containers iterate more quickly and at their own pace. And this streamlines both code deployment and infrastructure management. The process isolation lets you decompose your applications into whatever form makes the most sense and use Git-like tools with the Docker CLI to create those images and deploy them. The third advantage is that containers are quite fast. Now, simply stating that Docker images start fast could sell the technology quite short because speed is apparent both in the performance characteristics and in the application lifecycle and deployment benefits. So yes, containers start quickly because the operating system's already running, but every container can be a single-threaded development stream, so there's less interdependencies among your development teams. There's also operational benefits. For example, your operation group can update the base image on which you're building your containers, like Ubuntu with whatever packages you want, and then you can just do a new Docker build and your developers just focus on their app, meaning it's much faster to develop and release. The third benefit that we see from containers is they're efficient. You can allocate exactly the resources you want, the specific amount of CPU, RAM, you can give it disk and network, and since it shares the same operating system kernel and libraries, containers use less resources than running the same processes on different virtual machines. So how might you use containers in the development pipeline? Well, first of all, your operation team can create certified base images with all the necessary patches and utilities. These base images can then be used to create utility containers. For example, a logging container, a Ruby container, MySQL, whatever it is that your development teams might need. And since Docker creates these images in layers, each of these builds on each other and can be versioned separately. Then developers can use these containers on laptops to build in their source code. And they do this by creating a container image using a manifest that's called a Docker file that can be versioned and shared with other people on the team. And then you can customize that image at runtime using environment variables. So you can use the same image for both development and test environments. So let's show this in action. I'm going to go ahead and log on to a server. And let's go ahead and create a new directory. And I have a nice little sample application that is here in a GitHub repository, which you can look at as well. It's a simple PHP demonstration app. And so we can just go ahead and git clone that and pull everything down into my directory. And so now I have a few different artifacts that are here on my local machine, one of which is my Docker file. And as I mentioned, a Docker file is really the manifest for how I want to build my Docker image. And so you can see some things that's pretty easily readable. We're going to start from an Ubuntu 12.04 base image. We're going to go ahead and get a few packages that aren't included, as well as update to the latest versions of the packages. I'm going to go ahead and add the source code that's inside my Git repository to var www. And then I'm going to set some environment variables inside there and expose port 80. And so when I go ahead and run this docker build command, it's going to go ahead and run through and build each of these images. And so each image gets built for each part of my, each line here basically creates a new image. And so that means that you can update your images independently. So for example, if your IT department basically created a new Ubuntu 12.04 that included some various packages, then that would be a separate image and it would just be pulled in. And so each of these is basically creating those separate images, and then at the end, Docker takes those images and pulls them together when you do your Docker run. And so we can see now we're kind of at the setting the environment variables section of our Docker file. Then it'll finish off with exposing port 80 and then running the command, the Apache server command, so that we actually will be able to see our demonstration app. Now, once we have the image, we actually have to do something with it, and so the way that you make an image run in a container with Docker is you use Docker run, and so that'll be the next command that I execute. And I could go ahead and push this image up to my Docker registry so that I could share it with my colleagues. So we'll go ahead and do Docker run. Basically say map the containers port 80 to my host port 80. And so now I need to just go and get the IP address of the instance that I'm using here. And let's go ahead and pull it up in a web browser and see what I've done. So now we can see the application that I started up on my container, on my instance, and that's pretty useful. It lets me do pretty quick and easy development work, and I can use the Docker push command to push that image when I feel like it's done. So as you can see, the Docker CLI is great, and it works really well, and is very simple to use, especially if you want to run a container on your laptop. But one thing that it gets challenging is when you want to scale to hundreds of containers, and now you're suddenly managing a cluster, and cluster management can be hard. For example, you need to find a way to intelligently place your containers on the hosts that have resources, and that means you need to know the state of everything in your system. For example, what instances have available resources like memory and ports? How do I know if a container dies? How do I hook into other resources like elastic load balancing? And can I extend whatever system I use to support my continuous deployment pipeline or third-party schedulers? And last, do I need to then operate another piece of software? And these are the questions that we wanted to answer when we developed Amazon ECS. We spoke with customers that were trying to run Docker containers and felt that we could make the process a lot easier. And that's what drove us to launch Amazon ECS. So ECS has 4 key benefits. The first is that there's nothing else you need to run. Running modern distributed applications on a cluster really requires 2 key components: reliable state management and flexible scheduling. And these can be challenging problems. Amazon ECS handles the complexity of cluster and container management, so you don't have to install and operate your own cluster management infrastructure. At Amazon, we've built a number of core distributed system privileges that support our needs, and Amazon ECS is built on top of one of those primitives. We then expose this state management behind a simple set of APIs that give the details about all the instances in your cluster and all the containers running on those instances. The Amazon ECS APIs respond quickly whether you have a cluster with a single instance and a few containers, or a dynamic cluster with hundreds of instances and thousands of containers. So what is a scheduler? Well, a scheduler understands the needs of the system. That is, the work that needs to be done, such as starting a container that needs 200 megabytes of RAM and port 80, and looks to efficiently satisfy that. It then submits the request to the cluster state manager requesting a resource. Since ECS provides optimistic concurrency control, other schedulers could be operating at the same time, so the cluster management will confirm that the resource is available and commit it to the scheduler. The scheduler can then listen for events from the cluster manager and take action, such as maintaining the availability of your applications. It can also interact with other resources, like load balancers. Amazon ECS has 2 schedulers to help find the optimal instance placement based on your resource needs, isolation policies, and availability requirements. Create service and run task. And ECS provides you complete cluster state information, allowing you to integrate your own custom schedulers as well as open source schedulers. Amazon ECS is also built to work with the AWS services you value. You can set up each cluster in its own virtual private cloud and use security groups to control network access to your EC2 instances. You can store persistent information using EBS, and you can route traffic to containers using ELB. CloudTrail integration captures every API access for security analysis, resource change tracking, and compliance auditing. Finally, Amazon ECS can be easily integrated or extended through a simple set of APIs. ECS provides complete visibility and control into your AWS resources, so you can easily integrate and use your own container scheduler or connect ECS into your existing software delivery process. For example, continuous integration and delivery systems. We also have a blog that we launched a few weeks ago that describes how to create a continuous delivery process using Jenkins to create Docker images and deploy those images to ECS. Our container agent is open source and available on GitHub, and we look forward to hearing your input and pull requests. So now I'll describe a couple patterns that we're seeing from customers that are using Amazon ECS. The first is using ECS for long-running applications and services. Docker is really a natural for this pattern. It supports any application in any language. As you saw in my earlier demo, PHP, certainly you can add things like Ruby, Java, anything you can basically run on an EC2 instance today, you could throw into a Docker file as well and run that into a Docker container. You define everything that's contained in the image using that Docker file. So the Docker file ends up being a complete manifest of the image. So you don't have to worry about, oops, I made a tweak that I forgot to document, because everything that's inside that image has been documented in the Docker file, which you then can check into your version control system. And then the image itself becomes a versioned artifact that can be stored in a repository just like your source code. There's a number of different image repositories out there, and you can push your image once it's been built into one of those repositories, which makes it really easy to deploy and even roll back to previous versions if you need to. One of the things that's really nice about Docker as well is because it's so lightweight, you can then decompose your applications into microservices and decouple deployments to reduce conflicts. And containers also simplify deployments because of they're stateless. And stateless servers make it easy to deploy, make each new deployment a new set of containers. And so blue-green deployment patterns are very simple. By blue-green deployment, what we mean is that you can create a new set of containers that are for the next version of your application and spin down the version of containers that's running your current application, and then switch over the traffic from one to the other. And then you could always route back as well if you needed to roll back. The next common pattern we see is batch jobs. So instead of a dedicated pool of resources for each job, now you can use a shared pool for multiple jobs and increase efficiency, especially for short-lived and bursty processes. For example, Coursera is using ECS to handle the automated grading of programming assignments. Those assignments come in and are placed into the cluster, and they run in a container which can then be disposed of, and the instance is immediately reused by another container. So the compute resources, which are your EC2 instances, can use auto-scaling or spot or reserved instances and give you the resource mix that you prefer. In addition, since those are your EC2 instances, you can run them in VPCs and use whatever security group rules that you need for the particular mix of resources and jobs that you're putting onto your cluster. So let's go through a little bit about the Amazon EC2 container service before we go into demonstrate the EC2 container service itself. So the first thing is that EC2 container service, the containers run on your own instances. So these Amazon EC2 instances are inside your account. We have a optimized AMI that you can use that includes the Docker daemon as well as the Amazon ECS agent. And the agent is what calls back to the service and informs the service about the state of what's running on your instance. So what kind of resources your instance has available, what are the state of all the containers, and then it receives work from the service if you want to schedule containers onto it. You take those instances and you group them into clusters. And clusters are per region. And those are the pool of resources that you use to run your containers. So you can segment your containers based on cluster. For example, you might have a production cluster and a development cluster, or whatever other segmentation makes sense for your business. The other nice thing about these clusters, and what I'll show inside the demonstration, is that you can use things like EC2 auto-scaling groups, and as I mentioned, even things like Spot, in order to create the compute capacity for your cluster. The next component is what we call a task definition. And a task definition contains the set of containers you want to run together for a common purpose. So this is probably like your job that you're using or your application. It may just be one container, or it might be multiple containers that you all want to run together on a single instance. And so a task definition consists of 0 or more volume definitions and 1 or more container definitions. And so for our application that we're going to show in the demo, we're going to have a shared data volume, and we're going to have an application that displays data that's written to that data volume, and then another container that is creating the time of day. And I'm going to extend this application by creating a logging container as well to demonstrate how you can easily add additional containers to your task definitions to do particular things. And this container is going to be a shareable logging container that takes log files generated by your application and puts them into CloudWatch Logs. So let me just take you through what a task definition looks like so that you can kind of see some of the elements of that. So one of the components of a task definition is, for example, that you have the amount of CPU, the amount of memory, and here we have, for example, 10 CPU units, 500 megabytes of memory. You can specify the amount that you want your container to use. You also can specify the port mappings. So what port your application exposes on the container, and then what port you want it to be exposed on your host, the EC2 instance. You can also create and mount volumes. And so in this task definition, we mount a volume that's shared between our two containers. And finally, you can declare whether each container is essential for your task. So if one of the containers were to fail, do you fail the entire task? And if a task fails, then you can have the scheduler, the ECS scheduler, go ahead and reschedule that task for you. A few other parts of task definitions. This is our second container. You have a name for the container as well as the image that you want to pull. And so we're pulling the BusyBox image from Docker Hub. Docker Hub includes not only images that you push to your own repository, but they have a set of repositories that are provided by both Docker as well as ISVs like Ubuntu, so you can get certified images from third parties. And the command option is also quite important because it's how you can tell the container what you want it to do. So here we're basically in our time of day application, we're just basically writing what comes from our Linux date function right into our volume. So now that we have a task definition where we've defined the containers we want to run together and how we want them to share information, then we need to schedule that onto an EC2 instance. So as we saw, basically on my own server, I can just go ahead and do Docker run, but that sort of approach would be hard to scale. So we use a scheduler inside ECS to place that on an instance that has the appropriate resources, which in this case is memory. For example, I asked for 500 megs for my PHP app. It's ports because my PHP app is exposing port 80. So it's all the things the various constraints that I've identified in my task definition. And once we have a task, then that's actually the containers that are running. So it's containers that are doing something for you. And there's two ways that you can run a task in ECS. One is you can call the run task API, which is good for short-lived containers and containers that you expect to stop. So it might be a batch job that you want to run, and then once the job is finished, then you've put your output somewhere and the job's done. And that's different from a service where you have a long-running application that you don't expect to ever stop, or if you do expect it to stop, you want to control when it stops. So with a service, it will run the desired number of tasks, and if a task stops, it will restart that task somewhere else. The service also integrates with elastic load balancing, so you can route traffic from your ELB to the containers that are running in your tasks. And if an ELB health check fails, we'll also use that to stop the task that's health check is failing and start a new task. So you can know that all the number of tasks that you've requested are successfully running and healthy, so they're serving traffic to your ELB. With services, you can also scale them up and down, so you can change that number of tasks, say from 5 to 10. And I just published a blog last week on how you can integrate with CloudWatch alarms and Lambda to automatically scale your services up and down in response to those CloudWatch alarms. You can also use the service to deploy new versions. So if I changed the task definition version, say from here it's revision 1 to revision 2, then the service will take care of stopping the tasks running revision 1, waiting for your load balancing connections to drain, and then we'll start up the tasks running revision 2. So the service is quite a powerful concept for long-running applications and services. And one thing that's kind of nice about having services use ELB is that the elastic load balancing gives you an endpoint for your service. So you're able to get some basic service discovery by using the ECS list and describe APIs to list a service by name and then get the ELB that's associated with it. So now you can have one service find and connect to another service without having to hard code in any information about the particular ELB to the service name. As mentioned, easy to scale up and scale down, easy to deploy new versions and drain connections as well. So let's go ahead and go into the service and show a bit more demonstration. So let me go over to my console. And using Sydney today, because we just launched the Sydney region yesterday, with Sydney we now have support for Tokyo, the Portland region and Virginia regions in the US, as well as Dublin. And so if we go into my default cluster, we can see a few things. First of all, I have a number of instances that are part of my cluster. I've created these instances part of an auto-scaling group. So why don't I go ahead and I'll go into EC2 so we can just take a quick look at the capacity that's backing up my container cluster. So if I go to my auto-scaling group, right now I have it as with a fixed amount of capacity, but I certainly could create it with using an alarm to scale up and scale down automatically. I'm going to go ahead and increase this from 4 to 5 though, so make my max count 5 and my desired count 5. and we'll go ahead and see what happens. So I'll save that, and we'll go back over to my service, and just take a little look around the console at some other things, and come back, and we'll see this this count go up to 5. So there's a few other tabs here. One is services, and we're going to go ahead and create a service to run an application. We have tasks, which are the tasks that are running as part of my environment. And then we have task definitions. And as I mentioned, task definitions let us see the group of containers we want to run together. And so we have one task definition that's already defined here. And if I click into it, we can see that this is basically the simple app along with BusyBox. So let me go ahead and create a service from this. And we'll go ahead and create that in our default cluster, and we'll call this my webinar service. And we'll go ahead and just start up a few tasks here. And I'll connect it to an ELB. And I want that ELB to route traffic to my simple app. And I have to use an IAM role so that the ECS service can basically control your ELB. So we've given it the role to use, and I'll now go ahead and click on Create Service. So we can kind of see a few things about the service I created. You can see the ELB. You can see that I've asked for a desired count. Right now, there are 0 running. If I refresh this, we'll probably start to see that change. And there's a few different other tabs here, like we have an Events tab and a Deployments tab. So we can see that there's a deployment with the desired count of 3. The Events tab should start telling us a little bit about what the service scheduler is doing. So we can see, for example, that there are 3 tasks that have been started by the service, which is great. That's kind of what we were hoping. So those are pending. And if I look at the tasks, we can probably see those. Yep, and one's already running and 2 are pending. So we can kind of see that the service scheduler is doing its job at this point. It's getting the services up and running. It's by running the tasks that conform to my task definition. And if we go back to the cluster, we probably can see that we should have 5 instances now on which to run our tasks. Yep, so that 5th one that I asked to be started up is now actually running. So that's great. So we have a service that's running, and let's go ahead and go into that service. We could connect through the ELB, or we can take a look at each of these tasks. But the interesting part is less about the service itself, and I want to show a little bit more about logging with the container service. So we can see here, for example, the actual containers. We can see so we have our simple app and our BusyBox, and if I open this link in a new tab, we can actually see the app that I've deployed. So that's all well and good. What I'd like to do, though, is I'd like to update the task definition and include a new revision. So let's go ahead and click on this and create a new revision. And so the revision is going to include the containers and volumes that I already have. And just if you wanted to take a look at these, you can kind of click on these and see in the builder the container name, the image, everything that I've requested here. Scrolling on down, we can kind of see like the command, the entry point. If I were to set any environment variables, I could set those there. And then the volumes that I'm mounting between the 2 containers. I also can use JSON. So we can see here what the JSON representation of that UI is. And I've created a nice little JSON blob that I can now publish inside here. And makes it a little bit easier for the demo to do this quickly. And we can see that I have now another container name, which is called CloudWatch Logs. And CloudWatch Logs is a container that I've built. And all it really does is think of this as a log pusher that takes logs from a particular volume, and it pushes them to my CloudWatch Logs endpoint. Okay. So let's go ahead and save this as a new revision. And now let's go ahead and come over to my service, and I'm going to go ahead and update that. So now I'm going to switch to my CloudWatch Logs task definition and update the service. And we can see now the deployment. So we have one that's active, and then we want to switch over to the primary one. So we have 3 running here, but we want to have 3 running in desired. If I update this, we can kind of see the status of this as it goes along. So we can see now that we have kind of 2 pending over in the new deployment, and 3 still running over in the old version. And over time, this is going to go ahead and switch over till we have everything running in primary. And if we look over at the events, we can also see basically what's happening with the scheduler. So it's looking for places to start those tasks, looking for instances that are available and that have capacity for me to run my new tasks. Taking, it'll remove those containers as well from the load balancer, so it's taking care of all of the ELB integration as well with this. And if we wanted to, we could even take a look at the ECS instances themselves. And we can kind of see that one of the containers looks like it's been removed because the available CPU looks like we only have 2 tasks running. In fact, if we were to open these, we can see the tasks that are running. And now the CloudWatch Logs is pending on here, so we can see that some things are happening, whereas the sample app is still running on this container. So just gives you a little bit different window into what's happening. So we were looking from the service perspective, now we're looking from the instance perspective. So ECS is basically handling all the state management on your behalf. We'll go back into the service. We can see that the CloudWatch Logs containers are in pending. They're probably pulling down images from the repository. Meanwhile, your application is still running. So if I were to come back here and refresh, there's no change for the end user because we're taking care of making sure that your applications are running before we switch over the traffic on the ELB. And if we were to look inside the events, we could still kind of keep monitoring what's going on with the scheduler. So it's looking for places to place the task. Right now, I can't place that 3rd task because there's only 5 instances. And as we can see, 3 are still running the old version and 2 are running the new version. So until it can start pruning off the old versions, it won't be able to place the 3rd task that we want to have running. And we can see here that it's still running the 3 old versions and 2 are in pending. So now we can see that the CloudWatch Logs has moved from pending to running. And so now it's going to start draining connections from the old version that's running the console static app. And it'll also look for a place to place the new CloudWatch Logs once it's able to stop running the console static app. We can also switch over to take a look at our CloudWatch Logs console. So for those of you that aren't familiar with it, inside the CloudWatch console, there's a logs area. And as soon as those instances come up and get running with CloudWatch Logs, it will start placing information inside inside CloudWatch Logs for us to look at. We can see now that a couple of the console static apps have been stopped. So we're almost done with this deployment. We can see that it started the last CloudWatch Logs container that I need running. So we still have one running in the old version, and two running in the new, and one that's pending. So this kind of shows you an example of moving from version 1 to version 2. And so if I were to come back and basically put some traffic onto my application, we should be able to start seeing our log data coming through. Okay. A little demo error. I had it go to the wrong region. So I have my log container, unfortunately, pushing to US East. So we'll have to fix that little problem. But you can see that I'm now seeing the agent logs, the HTTP access logs, kernel logs, syslog, a lot of information that will be pretty helpful for me if I needed to debug problems. So for example, if my Apache server starts generating a bunch of 500s, I can use CloudWatch Logs to create some alarms for that, and then I can go ahead and dig into that. Or, for example, if maybe my container were to die, I can take a look at my Docker log and see what might have caused that. So now, instead of having to log on to my EC2 instances to get logs and find out what's happening with my service, I can instead just go ahead and look at the logs that my logging container is pushing up to CloudWatch Logs. And these are all being streamed. And so basically, as my logs get updated on my containers and on the EC2 instance, they immediately get pushed up here to CloudWatch Logs as well. And so you can kind of see the containers here with the container ID, the EC2 instance ID, and then what log file has been generated as well. So it's pretty easy then to diagnose where the problem's happening. I can then just go straight to that EC2 instance. So for example, 999B2545. We can go over to our ECS instances. And that's this one right here. So if we were to find a problem in our logs that corresponded to this EC2 instance, we could then click on that, find the EC2 instance IP address and SSHN if we needed to get more diagnostics perhaps. So that gives you a little bit of a sense as to how you might use CloudWatch Logs. We'll be publishing a blog on how to set this up yourself if you want to see more details on that. That'll be out in the next couple weeks. Hopefully this gives you a good sense, though, as to how you might go ahead and use containers together as part of a task definition so that you can run multiple processes that need to be run on the same instance for different purposes. Instead of running these all in one single process or single virtual machine, you now can split them up. And so you can have a group that's working on the logging container that's independent of the group working on your app, for example. So with that, let me go ahead and take